Hello, welcome to Material Science Lecture. In this lesson, we will continue our discussion on heat treatment for steel material. In a previous video, we talked about heat treatment process such as full annealing and normalizing, where we heat up materials, steel materials, for example, eutectoid steel. So eutectoid steel consists of 0.8% of carbon. So during full annealing and normalizing, what we did is we heat it up to a certain temperature above its transformation line from austenite to pearlite or austenite to cementite. We heat it up to transform all the microstructure back to austenite. We soak it at a certain temperature until all pearlite and cementite being transformed to austenite, and we allow slow cooling to happen for a transformation from austenite back to pearlite and cementite to happen. So this slow cooling happen at a continuous slow cooling rate. And then we also discuss about quenching. So quenching is when we heat up the metal up to austenite temperature, and then we soak it at that temperature so that all the microstructure transform to austenite, and then we rapid quench it to room temperature straight away. So in isothermal hardening, let us now consider what product or what microstructure that will be formed for this eutectoid steel. For example, when we rapidly cool it to a temperature below eutectoid temperature, but not at room temperature. So let's say the eutectoid temperature is 727. We rapid cool it to 700 straight away, and then we hold it for a certain period of time and let it isothermally transform. What kind of microstructure that will be formed? So this is what we call as isothermal hardening. So let's get started. By the end of this lecture, I hope that you will be able to understand isothermal phase transformation. You will be able to understand the formation of Bainite microstructure, and also you would be able to explain Martensite and Austempering heat treatment. So in a nutshell, isothermal transformation is a phase transformation which occurs at constant temperature. So during isothermal hardening, this heat treatment process is for plain carbon steel, where it is done by heating the steel until it becomes austenites and then quench it to exact temperature and left it there for a specific span of time. During this heat treatment, the microstructure transforms into a combination of different microstructures. So this isothermal transformation can be described using what we call as TTT diagram. So TTT diagram is referring to time temperature transformation diagram. And how is this diagram is being made? Is through a process where a number of thin discs made of the same steel. In this example, I am using steel with 0.8% of carbon. So this is a eutectoid steel. So the first thing that the material scientists did is they put all these discs with the same composition in the furnace, where it will be heated up to a temperature above the austenization temperature. So for eutectoid steel, austenization temperature is 727 degrees Celsius. So at room temperature, we will have this steel with a microstructure of pearlite, which consists of ferrite and cementite phase. So above this temperature, everything will be transformed into austenite. And the second step, what they did is to transfer all of these discs into a second set of furnace with a temperature below eutectoid temperature. So, for example, at 700 degrees Celsius, and they will hold it. They will hold this eutectoid steel at this temperature for a certain period of time and let the transformation happen isothermally. But with these 5 different discs, they want to see how much percentage of the austenite has been transformed into pearlite at certain period of time. So they want to see, let's say after 6 seconds, how much of the austenite has been transformed. And after 22 seconds, how much of the austenite has been transformed to pearlite. So to do this, what they need to do is for different discs, they will need to quench it to a room temperature straight away after a period of time to see what's happening with the microstructure. So they want to see what's the microstructure that happened after 6 seconds. So what they need to do is they take that first disc after 6 seconds out of the furnace and quench it to a room temperature. And under the microscope, they can determine what is the transformation that's happening after 6 seconds, being whole at the temperature that they choose in the second furnace. So this microstructure observation is done using optical microscope. So what they did first is they austenize it to a temperature above eutectoid temperature and then quench it to 700 degrees Celsius. And they will look at the transformation happen at 700 degrees Celsius at a different time. So they start with at 0 time equals to 0 second, everything is still in austenite microstructure, austenite phase. And they will let the first disc to run to be whole in that temperature for 6 seconds. And then they quench it to look how much has been transformed. So now, if they look under the microscope, what they can see is that some fraction of the microstructure has been transformed into pearlite for this temperature 700 degrees. Some has been transformed into pearlite, the rest still retain the austenite. So this doesn't really matter. They just want to see how much fraction has been transformed from austenite to the different microstructure or different phase. And after, let's say, 20 or 18 seconds, what you will see, what you will observe, they do the same thing. After 18 seconds, they take it out from the furnace and quench it and look at the microstructure. The fraction that has been transformed, so this is the second disc that has been transformed, is a little bit more. And they carry on until what they can observe is after 67 seconds, all of this steel, the disc has been transformed into pearlite 100% throughout the volume of the disc. So using the optical microscope, they can observe this transformation. So using this isothermal data at 700 degrees Celsius, or here I will call it as T1, they will identify the start and the finish time of the transformation. So they will plot this data into the fraction transform versus time graph. So here, at this point here, the transformation from austenite begin, and here the transformation from the austenite to pearlite for our example, previous example, this will end here. So 100% of the microstructure or 99% of the microstructure will transform at 700 degrees Celsius after this period of time here, after it reached, in our example, 67 seconds. Okay, so this is only the data for 700 degrees Celsius. So what they need to do, what they will do next is to try it at different time. So using the isothermal data at T2, let's say if they hold that materials from austenites, they quench it to a temperature below the first one, below 700 degrees Celsius. So they use the same steel with 0.8 weight percentage of carbon, but now instead of 700, they quench it to 600, for example. They will start to observe again when the transformation begin and the transformation end. It won't happen at the same time. So for lower temperature, the transformation will begin quicker than the above temperature. So here, the transformation happen after a few seconds earlier, then the transformation happened at 700 degrees Celsius, and it will end earlier as well. So using all this data, what they will do is that they will plot the start and the finish time to develop what we call as a C-curve diagram or TTT diagram. So this is how the TTT diagram look like. So for T1, the transformation begins at this time and it will end at this time. So this axis here represents time. This axis represents temperature. For a temperature that is lower than T1, for example T2, it will begin here and it end here. So they repeat the same experiment but at different isothermal temperature. So they probably will do another one which is T3, and it has this curve in the fraction transform versus time graph, and they transfer the information, the data from this graph to the other graph, and they observe that for different temperature, for let's say T3 here above T2, it will begin here and it will end here. So they repeat the same experiment over and over at different temperature, at different holding temperature, to create or to construct this C-curve diagram. So the data that I gave you for the experiment in the previous two slides is not the real data. It's just an example to give you some insight on how this diagram being constructed. So the real isothermal transformation diagram or the TTT diagram of eutectoid steel look like this. So from this data, from the data that they have gathered from these various isothermal transformation temperature, they come up with this TTT diagram. So if you have a look at this eutectoid steel, if we do this isothermal transformation at 600 degrees Celsius. So first thing, during this isothermal hardening, we heat it up to a temperature above the eutectoid temperature, where everything will transform into austenite. So if let's say we quench it to a temperature of 600 degrees Celsius and hold it at that temperature for a period of time, what you would expect is that after several seconds, which is here about 3 seconds, the first transformation to pearlite will happen. So this line here represents the beginning of transformation. And this line here represents the end of transformation. So after a period of time, it will transform 100% into pearlite. So from this diagram, a lot of information can be gathered. So as an engineer, if let's say you want to heat treat your material, you can refer to this TTT diagram. Here in this TTT diagram, it is already being denoted that if you isothermally transform your steel above this point, you will get a microstructure of coarse pearlite. If it's around this temperature, you will have fine pearlite. And at a much lower temperature, if let's say you have austenite here and you quench it to 400 degrees Celsius, what you would expect is another microstructure which we call as Bainite, which I will explain in the next few slides. And if let's say I want to, I quench it to a temperature below this line here, this is the line where Martensite will be formed. So if I, let's say, quench it to a temperature of around 200 degrees Celsius, I will expect my microstructure will all be in Martensite microstructure. And this Martensite microstructure is a diffusionless microstructure. So it doesn't require time. So what will happen instead is, after around this temperature at this line here, 50% of your austenite has been transformed into austenite, and at around 110 degrees Celsius, 100% of the microstructure is going to be transformed into martensite. So that's how you read the TTT diagram. So you can use this to predict your microstructure if you perform this isothermal hardening heat treatment process. So from this TTT diagram, we can observe that in a different range of temperature of isothermal transformation, we will predict, or we can expect, that we will have different microstructure. So between this range here, what we will expect is pearlite microstructure, either coarse pearlite or fine pearlite. So within this range, we would expect in our final microstructure, we will have bainite. All the microstructure will start to form when the temperature reach this line here. So this is begin, and this is the transformation end. So let's first have a look at the formation of pearlite in eutectoid steel. So I will erase all this, and I will use a chicken wire structure as to illustrate this. So here I have this chicken wire structure, and this chicken wire structure represent austenite grain. As soon as the transformation time reach the line where the transformation begin, the pearlite colony will start to transform at the grain boundary of the austenite grain. So at time step T1, pearlite colonies will nucleate at the austenite grain boundaries. And this transformation will happen, will start to transform, or will start to happen everywhere in that grain of austenite. So the pearlite will become bigger and bigger, and more pearlite will nucleate at time step 2, for example. So the existing pearlite colonies will grow, and the new pearlite will start to nucleate until at the end, after it reaches, so here in this third diagram here, at time step 3, you can see a lot more pearlite starts to transform from austenite, and until it reaches that line in the TTT diagram where the transformation ends, you would expect all of this austenite will transform into pearlite. So just by using TTT diagram, we can actually design the procedure on how we want to conduct our heat treatment. So if, let's say, you have eutectoid steel in your hand, and you observe in the microstructure, it doesn't have the size that you want, the grain size that you want. So you want to end up with a microstructure of pearlite with coarse pearlite, for example. So using TTT diagram, we can design the procedure on how we want to conduct this heat treatment. So for this example, we know that just by looking at TTT diagram, we can conduct it to a certain temperature where we will end up with coarse pearlite. So if, let's say, this is the temperature that we choose. So what we do is we heat up the steel that you have in hand to become austenite. So above eutectoid point, everything will be in austenite phase. And what we need to do is to quench it to this temperature and hold it at that temperature until the transformation begin and end. So just by looking at this TTT diagram, we know that after around, let's say, 40 seconds, so here, this time scale here is in log scale to fit all the information into one graph. So after 40 seconds, even without looking at the microstructure, we know that after 40 seconds, the first pearlite colony will start to transform from austenite. and we can predict that this transformation will end after around, let's say, 800 seconds here. So this is how we can use TTT diagram to conduct our heat treatment process. So depending on the transformation temperature that you choose, the pearlite can be coarse grain size or a fine grain size. So at a lower temperature, you would expect that the pearlite will be in a fine grain microstructure. At a higher temperature, it will be in a coarse grain size microstructure. This is again because of the diffusions of atoms. So here I have the example of eutectoid steel, the microstructure of eutectoid steel that has been isothermally transformed at 655 degrees Celsius. I have one at 600 degrees Celsius and 534 degrees Celsius and 487 degrees Celsius. As you can see, when you choose the isothermal transformation temperature at a lower temperature, you would expect a fine grain microstructure. So all of this information you can get from the TTT diagram. So just using the TTT diagram, you can predict what is the microstructure. And again, with prediction of the microstructure, we can predict what's the mechanical behavior of that steel that you will have, the final mechanical behavior of that steel. So if we look at the TTT diagram, what we can observe that at a much lower temperature range of isothermal transformation, we can expect a formation of a microstructure that we call as bainite. So within this range here, you would expect your final microstructure will consist of bainite. So here I will just explain a little bit on what is bainite. So bainite is a microstructure that consists of non-lamellar mixture of ferrite and cementite. So for pearlite, what we have described before, when the transformation of cementite and ferrite happen, it transforms simultaneously. So you would expect your final microstructure will consist of lamella of ferrite and cementite sitting next to each other. Whereas for bainite, what happened during the transformation is that ferrite will transform first. So at lower temperature, the needle-shaped ferrite will start to transform. And when you hold it at that temperature, this needle shape will grow bigger and bigger. But we also know that at lower temperature, the BCC ferrite cannot retain carbon inside the crystal structure. So what will happen is the carbon atoms will start to precipitate out of the grain boundary. So it will start to precipitate and it will form the intermetallic compound at the outside of the grain boundary of that ferrite. So your final microstructure is what we call as upper bainite, where the ferrite will transform at the outside grain boundary of ferrite. So this is how the upper bainite starts to transform. Whereas for the lower bainite, this happened at a much lower temperature. So what happened? It begins with the same transformation where ferrite will transform first in the needle-shaped microstructure. However, because of the low temperature, the atoms cannot diffuse out of this crystal structure. What happened instead, it will form the intermetallic compound of cementite inside the grains of ferrite itself. So the final microstructure, you will have what we call as lower bainite, consists of the needle-shaped ferrite with a small particle of cementite inside the microstructure. So at a higher holding temperature, it will give what we call as upper bainite, and at a lower temperature, it will give what we call as lower bainite. So I have here the bainite that form isothermally. So this is when bainite transformed from austenite at 495 degrees Celsius. In this microstructure, we can observe some still in austenite, and when the transformation happens, ferrite will start to form in a needle shape. You can predict that when this transformation finish, you will have this needle shape of ferrite everywhere, with cementite forming at the outside grain boundary of this ferrite here. So this is the upper bainite. Whereas for the lower bainite, you can see that during the transformation, the grain of ferrite here is much darker. This is because there is a lot of cementite compound exists inside the structure of the microstructure, the grain structure of the alpha ferrite. So this is lower bainite formation. So this first one is upper bainite. So just by looking at those microstructure, we can predict that the microstructure of the bainite will be much stronger, or the strength of those material will be higher if we compare to the pearlite, because the microstructure now will be much smaller, the needle shape, and also we have a precipitation hardening happen for the lower bainite. So we have precipitates inside the grain of ferrite. So we can expect that this metal will be much stronger than pearlite. So if, as an engineer, you have in your hand materials that consist of 0.8% of carbon, so this is eutectoid steel, and you want to transform them into bainite for certain applications. So you can use TTT diagram to predict or to design this heat treatment process, so that what you will get at the end, the microstructure that you will get, is a bainite microstructure. So what you need to do is to heat up your materials to become austenite again, and then quench it to a temperature within this range in this red box here. So let's say you transform it, you quench it to 300 degrees Celsius, you want to transform it to lower bainite. So you quench it to 300 degrees Celsius, you hold it for a certain period of time, your final microstructure will be lower bainite. The transformation will begin when it reaches 100 seconds, for example. So you can predict that your austenite will start to transform at this temperature here, around 100 seconds, and it will end at this time here. So around, what is that, about 3000 seconds, for example. So it will end at that after that time. So using TTT diagram, you can predict the time, you can set the time for the transformations to happen, and you can also predict what's the final microstructure of your steel, and in the end you can predict what is the mechanical properties of your eutectoid steel. So in the previous video, I've already discussed about the formation of martensite in eutectoid steel. So martensite formation is a diffusionless transformation. So what happens is that the atoms of carbon cannot diffuse out of the BCC crystal structure. It will retain in the BCC crystal structure, but what happens is that the BCC will expand it and the atoms of carbon will retain inside the microstructure. So what will be formed instead is what we call as body-centered tetragonal microstructure. So this is martensite. So the atomic motion occurs by cooperative homogeneous movement of many atoms that will result in the change of crystal structure. So again, using the TTT diagram, you can also use it to transform your eutectoid steel to become fully martensite. So for example, you have eutectoid steel that has been transformed into austenite, and we want to transform it to fully martensite. So what we need to do is to just quench it to a room temperature straight away. So what will happen is that the microstructure will start to form at a temperature of around 210 degrees Celsius. And all of the microstructure of austenite will finish transform to martensite at around 120 degrees Celsius. So you would expect at room temperature, your austenite will consist, or your microstructure will consist of all martensite inside it. So your microstructure again will be much brittle because of the formation of this martensite, which I already explained in the previous video. So this TTT diagram will not look the same for every other compositions of carbon. So the TTT diagram that I've shown you before is only valid to be used for heat treatment procedure if you have a eutectoid steel. You have a steel that consists about 0.8 weight percentage of carbon. So you can use that TTT diagram to design the procedure of your heat treatment. However, if you have different composition, let's say hypoeutectoid or hypereutectoid, it will look different again. But don't worry, if you work in this field where you have to conduct heat treatment, you can easily find a database for this different type of compositions of steel. So what I have here is the off-eutectoid isothermal diagram for hypoeutectoid steel. So for hypoeutectoid steel, we know that if we transform it by slow cooling, we will form pro-eutectoid ferrite first. So in the TTT diagram, it will be the same as well. So here, what you can see, there is a region where pro-eutectoid ferrite will be transformed first from the austenite. So the way to read it is the same as the way we read it using the way we read the TTT diagram for eutectoid steel. So here the pearlite formation is preceded by ferrite in the case of hypoeutectoid. And whereas for hypereutectoid steel, you would expect there will be this region here with cementite that will be formed first. So before I end this lecture, I would like to discuss a little bit more example on how we can use TTT diagram, in particular how we use the eutectoid steel TTT diagram to design our heat treatment process. So the procedure that the blacksmith used in the olden days to forge a sword is what we call as steel tempering process. So during this process, what the blacksmith did, if you have ever watched this whole process happening, is that they will heat up this steel. In the case of eutectoid steel, they will heat it up above the eutectoid temperature and transform all the phases, the existing phases, into austenite. And the next procedure, the next step is that they will quench it to a room temperature. So what they did is that they will rapidly cool it inside the water. So the temperature of austenite at that point, which is 727 degrees Celsius, will be rapidly cooled to a room temperature. And as what we have learned before, when we did this quenching procedure, what can happen is that the material will transform to austenite, from austenite to martensite straight away. So we know that martensite is a very strong microstructure. The material will have mechanical properties which is high strength and high hardness. But at the same time, this microstructure, the BCT microstructure of martensite, does not have slip plane. So we have materials with a very high brittleness. So what the blacksmith did, and if we look at people having sword fighting, the materials, the steel did not break straight away. So there must be a second procedure. So the second procedure is that the blacksmith will temper it at a certain temperature above the martensite stud formation. So they will hold that temperature for a certain period of time. So this is isothermal transformation. So this will allow the carbon inside the BCT crystal structure to diffuse out. So we actually soften the martensite at this process of tempering. And after that, they will allow it to cool to room temperature, and the final microstructure that will be obtained is what they call as tempered martensite. It is still hard and strong, but not as hard and as strong after the quenching process, but it is more useful because the ductility, some of the ductility has been restored. So the material now is useful for any application. But the problem with this process is that the outer layer or the outer structure of the metal, the steel, will be transformed to martensite first and followed by the inside structure of the metal. So this will create stresses or this will generate stresses and strain during this quenching process. So they come up with another procedure of heat treatment that they call as Martempering that will eliminate this effect. So Martempering process involves modified steel quenching procedure. This is to minimize the distortion that may develop during the uneven cooling of the heat treated materials. So in the case of eutectoid steel, it still begins with heating it up to austenization temperature. So in the case of eutectoid steel, we heat it up above eutectoid temperature. So all the microstructure will transform into austenite. And then the second procedure is that we quench it to a temperature above the martensite formation line, above this line here. So this is the martensite formation line. So what they did is that they quench it to a temperature just above that line. So no martensite will be formed yet. And they will hold it at that temperature until the inside structure temperature will catch up with the outside. So at this holding time, the structure inside and outside will have the same temperature by the time they end this soaking process here. And then what they do is that they will quench it to room temperature straight away. So all of the austenite will transform again to martensite. So again, with this, we will still form martensite, but with less distortion, less stresses and strain generated inside the materials. And as we know, martensite is very brittle. The next step is that they will temper it to a temperature above the martensite formation line and hold it for a certain period of time before they cool it down. The resulting microstructure will have a tempered martensite microstructure, which is much ductile if we compare to martensite, the initial martensite microstructure. So another heat treatment procedure that's being used a lot in the industry is what we call as Austempering. So Austempering is an isothermal heat treatment procedure that will produce Bainite as the final microstructure. So this heat treatment process provides steel with better toughness and ductility. So we will avoid the formation of martensite at all. So the process will begin by austenization. So the microstructure will be transformed, heat up, the metal will be heated up to austenite, eutectoid temperature, and the microstructure will transform into austenite, and they quench it to a temperature where then no bainite will be formed. So in this TTT diagram, we know that bainite will be transformed within this range. Depending on which bainite that we want to transform, we can quench it to any temperature within this range. And they hold it for a certain period of time where bainite will transform here and end the transformation of bainite there. At a room temperature, the microstructure will be bainite microstructure. So using TTT diagram, we can actually design our heat treatment procedure that will produce the final microstructure that will have a mixture of all of these microstructure. If let's say you want to create microstructure that will have Bainite and Pearlite and also Martensite, using TTT diagram, we can design this. I will show this with some of the tutorial questions that I have given you in e-learning. So in summary, what we have learned from this lecture is that isothermal transformation diagram will make it possible for us to predict the microstructural product for a specified heat treatment procedure. We've also learned that martensitic steel are the hardest and the strongest, and yet they are the most brittle. And we can reduce this effect of brittleness by tempering procedure. We've also learned that Bainite have high strength and ductility in combination, but it is not as strong as the tempered martensite. So using TTT diagram, we've also learned that we can design heat treatment process that will produce Pearlite microstructure, and Pearlite microstructure also can be divided into two, which is coarse and fine Pearlite that happen or that transform at a different temperature range. We've also learned about Martensite process, which is a process of heat treatment process that involve a modified quenching procedure that can eliminate effect of stress and strain generated from steel tempering process. And we also learned that in the industry, Austempering process can be performed. This is a process of hardening of steel, which will yield a desirable mechanical properties such as higher toughness and ductility. So that's about it for this lecture on isothermal hardening heat treatment process. I will continue in the next lecture where we will talk about continuous cooling heat treatment process. So until then, thank you very much. Thanks for listening.